some of us were talking about merging this. So welcome back. So the first talk is by my colleagues Sune, Niels, Cosmin and Troels, and Troels will give a presentation.
It's me again. This time I'm going to talk about something a little more low level. I'm going to show a parallel construct that I believe is necessary for a practical data parallel language, and I will argue why, and show why I think this is necessary. And then I will show how to efficiently implement it on GPUs. And this is work in progress, so there are some things that don't work quite as well as they should yet, but I think I will manage to get the idea across. So let's consider computing a histogram. So in a histogram, we are given some constant k and an array of n integers, and we are asked to produce an array of k integers, hist, where hist at position I counts how many times I occurs in the IS array. So visually, a histogram is something you've probably all seen before, where we count number of occurrences of each bin in the histogram. It turns out that this is actually surprisingly tricky to implement in a functional and parallel way. So in an imperative language, it's pretty straightforward. We just initialize a hist array with k zeros, and then we have a for loop all across the input. And for each IS, we take out its value j, and we increment the corresponding location in the hist array by 1. The amount of work here is O of k plus n, k to initialize the histogram, n to run through the input array. There'll be some cache issues on larger arrays, but we'll ignore it. That level of detail is not really where we find the problems. Now the problem is that this is not parallel, this is a sequential for loop, and it's not functional because it uses in-place updates of the array hist. So we can write a data parallel implementation. I'm going to show it in Futhark, but there's not really anything Futhark specific going on here. So I have a function histogram that takes an array of n integers, is, and a constant and a value and an integer k, and produces an array k. And the histogram is then produced by first producing a bunch of one-hot vectors. So for each element in this is, we produce a vector that is all zeros, except at place position I, where it's 1. And then we do a reduction, where we just sum up all of these vectors using ordinary vector addition, and this will give us a k element vector in the end. Now the big problem is that this is O of k times n work, because we are constructing k element vectors, and we're constructing n of them, and we're summing them all together. So it's asymptotically less efficient than the sequential implementation, which is bad, because it means that when the input size becomes large, the sequential implementation becomes faster than the parallel implementation. We don't want that. Now it does have O of log n span, which is good. So span is a measure of the longest chain of sequential dependencies in the program. So it's a measure for how parallel the program is. We want as low a span as possible. The O of log n span comes from the reduce, and it can be shown. I'm just going to claim that reduce has O of log n span here. When math, for example, has O of 1 span because there are no dependencies for computing in math. Okay, so this version is kind of unsatisfying. Another way we could compute a histogram is by putting the map on top. So now instead of constructing all these one-hot vectors, what we are doing is that we are mapping over each of the k buckets in the histogram we want to produce, and then for each of those we count how many, for each of these j's, we count how many elements of ys are equal to j, and to load them to ones and the others to zeros, and then we sum that up. Unfortunately, it's exactly the same as before. It's still O of k times n work and O of log n span. You can actually derive these two from each other just by interchanging the maps and the reducers. So these are not very satisfying solutions. A theoretically efficient implementation it looks like this, where we first sort all the indexes with a radix sort or whatever other sorting algorithm we want, but we use radix sort to make the constants and make the asymptotics work out. Then we compute when do we switch from one bin to the other, so when are neighboring elements different in the sorted array. This can be done with some map and rotates. And then we do a segmented reduction where we are sort of summing up each chunk of equal elements, so counting up how many occurrences exist. So this is O of k plus n work. It can be shown by and this is because the radix sort is of course linear time. That's why we need it to be a radix sort, not a merge sort. And the segment reduces also linear time. The span of O of log is O of log n, because that's the span of the radix sort and the segment reduced, which again I'm just going to claim, but can be shown pretty easily. So this gets us the asymptotics that we want. The same asymptotics as sequential implementation, which is what we call work efficient, and it's still probably as efficient as it can be. I don't have a proof that this is the lowest possible span, but since it's kind of similar to a reduction, I think this is going to be the lower bound. It also assumes the bins are non-empty, but that's not a big problem. The problem is that this radix sort here is really slow in practice because it needs to traverse the entire input multiple times in order to put all of the elements in order. Asymptotically efficient in practice, not so much. So can we do better? Now the tragic thing here is that the hardware we're running on, for example GPU or for that matter CPU, it does actually have very efficient operations for atomically updating the bin counts and the histogram we are constructing. So we could, in principle, just have our original for loop, launch one thread per input element, and then use these atomic operations to safely update the elements of the histogram without any risk of race condition. We can't expose these constructs directly in the pure functional language because they are side effecting. So we don't really want to expose those. So what we need is a language construct that has pure semantics, no non-determinism or anything like that, but which can internally exploit operations like this. This construct is one I've called reduced by index. So it's polymorphic in that it takes first an array of k a's. So this should be an a. So that's only one scalar node. So an array of k a's. And then a combining operator, binary operator from A to A, which must be associative and commutative. Then another A, which must be a neutral element for the operator. So for example, if this is plus, this must be 0, and if this is multiplication, then this must be 1. And then it takes an array of n integers and an array of n values. And then the semantics are given by this sequential loop, where we go through all of the n inputs. For each input, we fetch out an integer for telling us which bucket and histogram to update. Then we check whether it's in bounds, and if it's in bounds, we use the provided operator, f, to update that location in the histogram, which it can be addition, but it can also be something more interesting. This bounds check here is, it's not critical, but it's often convenient to ignore out of bounds right in some algorithms, because that means you don't have to filter them out, or can then just turn them into -1s and they'll be ignored. But it's a small convenience. Now, the nice thing is that this histogram, this update here, where we perform an in-place update to an array, that can now be implemented using atomic operations. And in our code generator, we look at what f looks like statically. And if f corresponds to something that has a dedicated atomic operation, like an integer addition or an integer of minus, or a field that has a small list of things that have specialized functions, then we use those functions. And that's the best case. Those are the most efficient. Alternatively, if f is some crazy operator, but it operates on 32-bit values, then we can use a trick with a comparative exchange where we read the current value, then we compute the new value, and then we do a comparative exchange where only if we still have the old value in the place we're trying to update do we write our new value. Otherwise, we just we start over again and try again. So this is kind of a spinning on the histogram. Until we are allowed to update it, we keep on looping here. That's pretty efficient because the atomic comparative exchange for 32-bit values is efficiently hardware accelerated. In the absolutely worst case, if f is something completely nasty or some weird type that doesn't have any efficient implementation, then we fall back to your usual spin lock with a compare and swap instructions, which is pretty expensive, and you need an external array of logs to synchronize it. But you can make it work, and it will be deterministic and safe and all that. Now, the performance then looks like this. So this is for a fixed n, 1 million input value pairs, where we then modify k, the number of bins in the histogram we're constructing. And what we can see is that the map reduce I showed you, the performance is completely linear in k, which is as expected since it's O of k times n. The sort plus segment reduction scales pretty well, but in terms of absolute performance, it is completely crushed by the efficiently reduced by index that uses hardware atomics. We can't even see that the reduced by index here slows down as k increases. It does slow down slightly because of cache effects and other things, because we have a larger histogram array we're writing into, but it doesn't start to really be noticeable until way out here, where if I plot it all the way out there, then the map reduce will not be visible anymore. Okay, so this also shows the difference between theoretically efficient and efficient. And this is why I think that a language construct like reduce by index is necessary, because otherwise you have to live up here, and that's kind of wasteful, although in theory it shouldn't be. Now, what I've showed you so far is not really novel. Accelerate, that Trevor talked about this morning, also has a construct much like reduce by index, which is called commute. The main difference is that instead of an array of index values, you pass it an index transformation function. But since this function can just use the index passed in here to read another array, there's not really a difference. This is almost isomorphic. Well, it is isomorphic. And the implementation is also very similar. I don't think it uses the compare and exchange trick, but otherwise, again, it pattern matches the function, uses efficient atomic objects if possible, otherwise falls back to spin class. Now, there's still a problem. I mean, atomics are not magical. If lots of threads are hammering on the same histogram element, then you still have contention. The only thing you get is that the hardware sequentializes them for you and gives you a predictable ordering, or not predictable, but some well-defined ordering. So let's see what happens when we try to compute histograms with different k-size, different bin counts. First, we try with an atomic add. So we want one of these operations that are really efficiently implemented in hardware. And we can see that if we try to compute a 2000 element histogram, it will run in 2.5 milliseconds. With a 1 element histogram, it takes 2.2 seconds, which means it's actually faster with a small number of bins, even though we have more conflicts. I think this is this is generally the case on most of the GPUs I've tried, and I think it's because the atomic adds are efficiently handled by the memory subsystem and automatically reorder or something. Because this is semi-magical. Here we have a config of every single update. It really so the GPUs really know what atomic adds mean. Like they're really savagely optimized. And the reason it's faster is probably some cache effect, where we just have a smaller array we're writing to, so it can stay in cache. So let's try a more complicated operator that is not natively supported, specifically 64-bit integer addition. This will have to fall back to the spin lock case. I'm just turning all the values into 64-bit integers here. And I'm still using 2 values of k. So here we see the effect of completely sequentializing the updates. Because now all the threads are just waiting on each other for these updates to occur. And this can get almost arbitrarily bad on larger n and on different GPUs. So we have a problem. Lock contention is real. So the solution that we're investigating is to, instead of computing one histogram that every thread is hammering on, we are computing multiple subhistograms. We divide the input elements into chunks of various sizes. And then for each of those chunks, we compute some subhistograms, which are then partial results, which we then combine into a single histogram at the end using a segmented reduction. So this means that we are cutting the amount of conflicts proportional to the number of subhistograms that we are using. And there's an additional trick this enables, which is now we can, since we have some locality in how these are computed, we can play around with where the subhistograms are located. For example, the atomics I showed you before, we're putting a single result histogram in GPU global memory. But now we can do things like grouping these into GPU work groups, which are small assemblies of threads that can collaborate. And then they can collaborate on something that is called local memory, which is a small unchipped user-controlled cache that GPUs have, that is much faster than ordinary memory, but can only when it's only coherent within a small number of threads, around 1024, but which is very fast. And it's also very limited in size. You have like 64 kilobytes per streaming multiprocessor on the GPU, so not all subhistograms will be able to fit in local memory. So we have some this complicated formula that is based on, well, how much local memory can each thread use without reducing occupancy, because if you use too much of it, then the GPU can have fewer threads in flight, and other threads have to wait, so you lose parallelism, which we don't want. And we have some notion of how big should our work group be, and how many GPU work groups should we have, so how should our thread topology be, and how big is a single subhistogram, and how large can local memory be. So we have a formula that tries to say, well, if we can fit subhistograms into local memory at all, and if it doesn't affect occupancy too much, then we put all the subhistograms in local memory, and then When they're done, we put them in global memory and compute the final result. Otherwise, we put the sub-histograms as well in global memory and collaboratively construct them there. And this formula is basically heuristic based on what we have observed to be efficient in practice. So now we can try these things again, and we see that, yeah, it's let's take this case first, the case that was 800 times slower before. Now it's actually faster with k equals to 1, because these sub-histograms here, the one-element histograms, are tiny. They will all fit in local memory. So now we're not even hitting global memory here at all, which is efficient. Whereas for k equals 2000, we still need to put the partial results, the sub-histograms, in global memory. We see a different result up here, and that is because while it is true that now the sub-histograms fit in local memory for the integer addition as well, that doesn't make much of a difference because atomic adds, even on global memory, are so efficient. And now we pay the cost of this final reduction here, which we didn't before. So, so it affects it affects sort of which things are fast, but not so much. This is still pretty. We now have a very lovely case that even for nasty operators, the performance is a lot like the most efficient case. Now it's not. This doesn't fully solve the problem because we still have an issue where k may be large, but if only a few indexes are hit, we still have a problem where we can have very few sub-histograms because they wouldn't fit in memory otherwise. But all the threads are still hammering the same location, the same bin in the histograms, which will then be inefficient. We haven't solved that yet because it turns out it doesn't turn up very often in practice. So, but in the most degenerate cases where you have completely unbalanced bin hits, the sort and reduce case may be best. It will actually scale perfectly. And we also work on various other techniques because we won't have to write a paper about this, where we chunk the input and make multiple passes to try to reduce the conflicts based on first running an inspector to estimate how many conflicts we will have. But this is not really implemented yet, and it's except in a manual prototype, and I don't think it's really worth it for most real programs. We tried comparing our performance to COP. COP is a CUDA library of heavily optimized primitives, generally considered to be the best or most performant set of library primitives for CUDA. With COP, you do need to do this radix sort plus segmented reduction thing, so compute histograms. It doesn't have a native histogram except for integer addition. It's not for any of these more complicated cases. And we see that Futhark actually beats COP in all cases, although it's quite impressive that for things like double addition, which falls back to the spinning up, COP will have to do the sort and segment reduce, and it's not actually that much slower than Futhark, because, yeah, while radix sorts are not great, COP has a really good radix sort. So, but we can still beat them slightly. And this, of course, this is for uniformly random. This is for randomly uniformly distributed bins. So this is without many conflicts. If you had many conflicts, then COP would be the hell out of Futhark because their sorting and reducing is completely invariant to conflicts. Okay, so in conclusion, I think a reduced by index like construct, no matter what you call it, is necessary if you want to efficiently support histogram-like computations and make them fast. I think sub-histogramming, even the simplest case, is most of what you need. I think the basic idea of just using more than one sub-histogram is in almost all cases enough. But there are degenerate cases where you need this sort reduce thing. And I'm a bit split on whether the compiler should automatically insert a check and branch to a sorting-based implementation, or whether it should be up to the programmer to know when it's possible to hit these degenerate cases, because it doesn't really happen often in practice, as far as I've seen. Okay, so that was my presentation.
Questions?
So it used to be the case, I don't know if it still is, that spin locks on GPUs were not guaranteed to you weren't guaranteed progress because the scheduler, a hardware scheduler, might just keep running the spinning code forever.
You need to be very careful with your atomic memory fences. I have stalled a lot of GPUs during this work. But NVIDIA does use this trick themselves in some of their code, and they kind of augmented their spec to say, if you do roughly this, then we promise it will kind of work.
More questions?
Is it easy to generalize to sort of multiple levels of histogramming, like multiple indices, or
we just flatten out the indexing.
that's what in your use cases.
Yes.
Is always like.
Yeah, but whenever we had use for 2D histograms, we just flatten out the indexes using row or column feature. I don't know if you can sort of do something smarter there. I don't know if there's an advantage to it. Maybe there is.
Short intermediate question. It's not staged, even though we're colleagues. So you showed the 64-bit one. I mean, first question is like these atomics. Are they working for operations or non-commutative?
No, because they're inherently lazy. You have no idea which thread comes first.
Okay, so they're only basically
yes, and
just
floating
getting them all
point is not,
executed.
so floating point is of course not commutative, but it's sufficiently commutative that you get useful.
Sufficiently commutative. All right. So just you get 64-bit. Could you do some kind of tricks with actually treating them as pairs of 32 bits?
No, because you really need it to be transactional. You can't just replace the two 4-byte words by themselves. I think you can do something, but it'll fall back to being as inefficient as the spin one. Now, I should mention that this is kind of artificial because GPUs do actually support 64-bit atomics. I just pretended they didn't have an example here. But there will be, then you can have more complicated values that they don't support.
20 values next time. So, more questions? Okay.
For your applications, did you have a lot of examples where you actually needed those complex operations?
Yes. Yes. So one of the examples we had was there's a benchmark suite called Parboil that computes a histogram where the operator is saturated position. So when it hits the maximum integer, it stays there, it doesn't overflow. And that requires the compare and swap thing, not the spin lock, but the other one.
But in your, like in the finance application, some you have, but not benchmarks.
No, we haven't found this in finance, I think. We find it in graphics because when you do rasterization, you can use this to implement your set buffer. So taking the nearest pixel, that's probably the most fancy example because it makes pretty pictures.
It's also, I think, useful in k-means.
Yes, but now you have atomic addition, so it's a simple case. Well, you have vector atomic addition, but you can detect that as well. Yeah, for k-means it gives about a factor of 2 or 3 performance improvement.
Histograms are basically they're just basically computing the inverse of a function. So are there examples? That's got to be useful in many cases. Can you have more applications? We've just mentioned some where that's useful and important to get right.
In general, I think it's extremely useful. I think the guy gave an example where you need a very complex.
The most cases are the simple ones, but it's nice that they're complicated.
No, it's very nice work.
You haven't mentioned machine learning yet. I'm just.
I thought you were leading up to it.
Yeah. Well, I think that's that. Thank you very much.